Hello, and welcome to the 2021 MEF 3.0 Proof of Concept Showcase, where MEF members collaborate to demonstrate MEF 3.0 based use cases that validate, evolve, and inspire the work of MEF. I'm Kevin Vachon, your host, and today we're showcasing POC 138, entitled End-to-End Slicing for Extreme Services with NTT Communications, NTT Labs, and Okinawa Open Laboratory. Extreme services over network slices and 5G sounds very intriguing. And you know, I saw Daniel Barlev's LinkedIn post a little while ago with this sketch of showing sharks and surfers and thieves and drones. And I thought, we got to see what this thing is all about. I really like the job you did there, Daniel, by the way. But anyway, let's find out more about these extreme services. We're going to kick off with an introduction to the POC by Yukio Ito, who's the chairman of Okinawa Open Laboratory. Will be followed by the demonstration itself, a panel discussion, and then a Q&A session. And you can queue up your questions at any time during the event by selecting the Q&A tab on the right. So let's get started, and we'll hear from Yukio.
Good morning, good afternoon, good evening, everybody. My name is Yukio Ito, a chairman of Okinawa Open Laboratory. I'd like to introduce the overview, background, and goal of our POC. Our POC aims to provide our customers with the extreme services over end-to-end multi-layer slices utilizing with LSO orchestration. This POC demonstrates the next innovation and directions in end-to-end network slicing. Powered by a service orchestrator, together with multi-layer transport and 5G slice controller, slice gateways, and high-accuracy network monitoring systems, end-to-end network slicing across different domains can be instantiated to enable high-performance network service for mission-critical applications. Functional specific dedicated networks over multi-layer and multi-domain network is orchestrated the simple SLA-based service ordering and control using service automation in alignment with MEF LSO framework. The global market is driven by the growing need for ultra-reliable low-latency connectivity for industrial IoT applications, including collaborative robots, industrial cameras, and industrial sensors. The demand for time-sensitive networking, TSN, and reliable real-time based networking is rapidly increasing for several mission-critical applications across many industries, including manufacturing, oil, gas, and social infrastructure, such as transportation system. Thus, to provide high-speed bandwidth connectivity during TSN and real-time networking across industries, the demand for private 5G network is anticipated to witness significant growth over the forecast period. Network slicing provides the ability from the radio access network side to 5G cores to allocate wireless performance resources for a given subscriber's slice. While 5G promises many advanced capabilities, it is only wireless access and mobile technology. Without end-to-end slicing, we will not be able to effectively manage 5G-enabled services from the radio access network to the 5G core and many existing wired network infrastructures. This POC has been established to demonstrate the next innovation in end-to-end network slicing over private 5G and WAN with the following goal. First, automating service provisioning lifecycle management, network slice provisioning, and end-to-end assurance across private 5G domains and transport network domains. Second, showing how network slice performance can be measured and monitored with an end-to-end view. Third, using established MEF LSO APIs, including Sonata, for inter-service provider service and slice ordering, as well as PREST between SOF and ICM for transport and 5GC. The aim is to provide MEF with variable feedback to advance and mature the PREST API to enable network slicing. Fourth, demonstrating the network service over end-to-end network slice and its performance assurance to support mission-critical use cases. The aim is to show enhancements of MEF service definitions for network slicing. Finally, following last year's MEF Awards, NTT, Okinawa Open Laboratory, and NTT Communications are working very closely to take part in this POC. Thank you very much.
In this POC, we will introduce the technology to realize more advanced and stable end-to-end enterprise network services by linking private 5G and network slicing. Private 5G is said to make it possible to build a more secure, high-performance and stable mobile network for mission-critical applications using wireless communication. 5G introduces network slicing that can provide networks of different performance characteristics. 5G network slicing, which was first discussed in 5G, is now attracting attention as a technology that enables assured and secure connectivity to MEC or cloud over the transport network and will create new services over end-to-end network beyond 5G. For example, there are use cases such as high-capacity communications for AR/VR systems, remote machine control using AI, and infrastructure for securely transferring data from IoT devices to the cloud. Until now, 5G and transport network slices have been developed as separate technologies, but slicing in their individual domains separately cannot immediately provide guaranteed end-to-end services. In this POC, we will show that end-to-end network slicing across the two domains is possible, and that it is actually possible to provide assured and immediate communication services for mission-critical applications. This POC demonstrates the next innovation and directions in E2E network slicing, which accelerates implementation of an orchestrated and assured multi-domain network slice and extreme services on it through automated resource provisioning and network activation. Powered by a service orchestrator together with multi-layer transport and 5G slice controller, slice gateways, and HANMC, E2E network slicing across different domains can be instantiated to enable a high-performance network service for mission-critical applications. Functional specific dedicated networks over multi-layer and the multi-domain network are orchestrated, activated, assured, and managed using simple service level agreement-based service ordering and control using service automation in alignment with MEF's LSO framework. The network environment for this POC is comprised of 3 organization domains. In the NTT domain in Musashino, cloud-native 5G functions are running on 2 Kubernetes clusters, and the slice gateway identifies the slice and distributes it to the slice on the segment routing-based transport network between the Kubernetes clusters and NTT Communications. Similarly, in the NTT Communications domain, 5GC, AI, and storage applications run across the 2 virtualization platform. The slice gateway distributes traffic to appropriate transport slices using segment routing. In addition, HANMC is located at the Tomachi site and monitors the latency and jitter of the entire network including Musashino and Okinawa. The Okinawa Open Laboratory environment in Okinawa is running 5G cores as Docker containers, and Marine Life Identification AI is running. The NTT and NTT communication sites are connected by several paths of different layer transport, which are used as slices according to the SR functions. Okinawa and Tomachi sites are connected by a leased line. Finally, these three multiple sites and clusters across Japan are managed and controlled by single controller and orchestrator. E2E slice controller from NTT acts as ICM in LSO framework and enables integrated control and management of E2E slices across 5GC and transport domains. Also, the service orchestration, SOF, is implemented with the product from OOL. In this POC, in order to protect safety of tourists swimming, which is the tourism issue in Okinawa area, we will demonstrate application that takes video of the sea with underwater drone and analyzes the images to identify dangerous creatures. Before demonstrating end-to-end slicing, we will show how the 5GC slice with different performance is instantiated and the difference in detection accuracy of AI to reveal the effectiveness of network slices. In the demo, when the orchestrator receives the invocation of the 5GC slice via the LSO API, it generates two slices, one that connects the 5GC slice to Tokyo by default in the domain of OOL, a private 5G provider, and the other that connects to edge computing for low latency AI processing. The video of the lionfish will then be sent to the two slices for AI analysis and comparison to see if it can be detected correctly. The private 5G provider signs into the order portal and places order of connectivity with private 5G core to application on near edge data center. To perform MEF LSO Sonata and Presto orders of access transport network to ensure the connectivity to cloud or edge required for applications using private 5G. Next is the order for Sonata and Presto for core transport network. Now let's execute in the end-to-end slice order. By issuing end-to-end slice order to the private 5GC provider and processing Presto there, the 5G core containers is being instantiated, and default slice and video application slice are provisioned. Users who want to use the video AI analysis contract SIM can use video application slice with the private 5G operator. The private 5G operator registers SIM information with available slice information SST and SD and DNN in the 5G core system. Now users can use video application slice with this SIM. Now let's compare the behavior of the video AI application that detects lionfish using default network slice and using video application slice. On the left is a demo video of launching the application using the default slice, and on the right is a demo video of launching the application using the video application slice. Using the default slice on the left, the effect of network latency is so great that the application cannot be launched. Using video app slice, the quality of the network is good, it starts up without any problems, and it detects dangerous marine life and notifies us with LEDs. Typical applications expected over E2E slices are shown to prove that mission-critical applications work in the demo system over created slices. The next use case applications are the real-time artificial intelligence for video analysis. The example requirements of video stream transmission over a network can be more than 200 Mbps per stream, and its latency should be 10 to 100 milliseconds to give immediate feedback to the camera or send alerts on the basis of the analytics. Now, the network slice order from customer including SLA performance objective in terms of throughput and latency arrives at service orchestrator. The 5G network slice instantiation is triggered at 5G slice controller by service orchestrator using Presto reference point. The service orchestrator requests transport network slice to transport service provider using Sonata interface. The transport network slice request is also triggered by a Presto, an E2E slice and multi-layer transport controller coordinates the path setup using slice gateway and handmake as well as segment routing. Now the slice instantiation started and is going. The GUI shows E2E slice instantiation status at the top one, and now the IP service over 3-segment routing domains is activated and 5G slice including dedicated containers for this service is instantiated. Now the end-to-end slice for this application is now created. After the instantiation of the end-to-end slice, we will demonstrate that real video analysis running on the network slice. This is the screen of the AI face recognition application. The application is running at the Cloud Edge site and recognizing the man's face real-time thanks to the high-definition stream and analyzes his gender and age correctly. This is the first demonstration of high-capacity and low-latency slice instantiation for real-time video analysis using AI or ML. The second service use case of end-to-end network slicing is RAN Mobile Transport, xHaul. The chart shows examples of performance requirement for RAN Mobile Transport are very severe. Latency should be less than 250 microseconds in front haul, and throughput should be less than 22.2 Gbps per RU owing to front haul protocol characteristics. For mobile mid-haul, the latency should be less than 10 milliseconds, and the throughput requirement is more than 4.02 Gbps per RU. For mobile backhaul, latency should be ideally less than 10 milliseconds, and the throughput requirement is more than 4 Gbps per cell or per RU. And then, the next demonstration of E2E slice instantiation for xHaul is now starting. The end-to-end slice order for MMH and MBH now arrives at Orchestrator, and Service Orchestrator initiates slice creation using 5G slice controller and end-to-end slice and multi-layer controller same as in the previous one. Now the network slicing is now being instantiated. In the slice provisioning status view, Ethernet connectivity for mobile mid-haul and IP service for mobile backhaul is now created in the third slice. Also, VCU and VDU is deployed and instantiated. Now the end-to-end slice including mobile mid-haul and backhaul connectivity and 5G slice including VDU and VCU is now created. Next, we gonna show the smartphones can connect to this network slice and download video streams from internet. This smartphone is currently trying to attach to the mobile network that just created, and as you can see, the signal sign shows up. This means this phone is now attached to the mobile network, and at the VDU, the smartphone signals are processed. Finally, the smartphone can connect to the internet and the throughput measurement started. The result is about 10 to 20 megabit per second as you can see in the smartphone screen on left hand side and E2E slice controller management console on the right hand side. This is the second demonstration of end-to-end slicing of xHaul. In the next demonstration, we will demonstrate the end-to-end network slicing for extreme services. The services we will show are TSN for remote motion control and RDMA for data center disaggregation. TSN stands for time-sensitive network, and TSN is used for local network, and the typical application is remote control of robots or automated guided vehicle, AGV, in smart factories. To implement precise robot or AGV motion control, TSN enables exact packet transmission scheduling in microsecond order in the local network, so normal delay variations are in the nanosecond order. By using network slices, TSN communications are enabled at the same level of delay variation as the local network, even if it is through a WAN. Another use case scenario is data center disaggregation using RDMA. As the disaggregation of server hardware in the data center progresses, server hardware like CPU, GPU, storage, and NIC will be connected over the network using RDMA, equivalent to computer internal bus over the network, such as PCI Express. RDMA can transfer data from the memory of a local computer to the memory of a different remote computer. An example of network performance requirements for disaggregated computing is more than 4 GB per second in throughput when in data transfers between memory and storage, and time synchronicity should be less than 10 microseconds for parallel processing between CPUs. In this demonstration, ultra-low latency and low jitter slices for TSN communication of robotic arm is created. Now, the network slice order for ultra-low latencies and low jitter has arrived at Orchestration. The order is divided into 5G and transport slices to create E2E slice, and each slice initiation starts. Now, the network slice instantiation is going. Transport slice with dedicated optical connectivity and 5G slice are instantiated for TSN communication. Now, TSN talker starts motion control signal transmission using TSN every 500 microseconds. TSN listener receives TSN frames from talker. The latencies experienced with TSN frame is almost 600 microseconds. The jitters, delay variations, are within 20 microseconds, so this means deterministic communication is achieved. That was the first demonstration. In the next demonstration, high capacity and low latency slice for RDMA communication is instantiated. Now, the network slice order for high capacity and low latency has arrived at Orchestration as same as last one. The order is divided into 5G and transport slices to create E2E slice, and each slice initiation starts. Now, the network slice instantiation is going. Transport slice with IPVPN using shortest path with guaranteed capacity and 5G slice are instantiated. The E2E slice for RDMA has been instantiated across 3 domains, and the end-to-end latencies observed is less than 5 milliseconds. Now, RDMA client attaches to RDMA server to storage data transfer using NVMe. RDMA attach completed, and RDMA client starts data transfer. Storage IOPS was 3095. It is equivalent to 24.2 MB per second. This is the upper limit of the POC network configuration. The throughput of the E2E slice is more than 200 megabit per second at maximum. The capacity and latencies are proven to be implemented at desired quality on the E2E slice. That is the technical demonstrations of E2E slicing for extreme services by NTT Communications, and OOL.
Thank you for the introduction, Kevin. My name is Hiroki Baba from NTT as the leader of this POC, and I will moderate this discussion between this panel. So in this talk, we have 3 organizations, NTT Com and NTT and Okinawa Open Laboratory. NTT Com as participating as service provider, and NTT is also a R&D department in NTT Group. And Okinawa Open Lab is an open source community and that solves local problems in Okinawa area in Japan. So today we have Hiroshige from NTT Com and Noriyoshi from OOL and me from NTT. So let's start with the discussion. So Hiroshige-san, could you introduce the significance of this POC as a service provider's view?
Of course. Okay. My name is Hiroshige Tanaka from NTT Communications. I lead network slice solutions and services project in the company. We think that network slice is one of the most important technology to provide our customers with the advanced end-to-end network service. When we say end-to-end, this includes private 5G, wide area network, multi-access edge computing, and cloud. This means multi-layer and multi-domain traffic control is needed. This is very complex and complicated, but if we achieve it, we could provide our customers with high experience and high value. In the first place, our company focuses on the smart factory market. For customers' automated guided vehicle, AGV is one of the key factors utilizing with private 5G. Needless to say, AGV is not only a carrier, but also a machine tool. If AGV could be controlled with private 5G remotely, the weight of AGV could be downsized, the batteries could be reduced, and the workable time could be lengthened. This increases the productivity, efficiency, and profitability of the factory. When we control AGV remotely, we have to handle several data traffic such as image analysis for motion control, data analysis for real-time compensation. Image analysis applications use 4K or 8K. The video stream should be over 200 megabits per second, and its latency should be from 10 to 100 milliseconds to give immediate feedback to the camera or send alerts based on the analytics result. Data analysis for real-time compensation uses a lot of sensor devices. The sensor data should be over 10,000 packets in a very narrow time slot. AGV is one of the use cases. Network slicing should be versatile in several industries, for example, smart health and smart city and so on. Network slicing requires the orchestration and the networking technology for end-to-end traffic control. In our POC, functional specific dedicated networks over multi-layer and multi-domain network is orchestrated, activated, assured, and managed using simple SLA-based service ordering and control using service automation in alignment with MEF's LSO framework, including Sonata and Prest. And we use segment routing for multi-path selection and connectivity control based on multi-layer transport resource management and automated optimal resource allocation for high network performance assurance. Our POC aims to harmonize these components utilizing with LSO orchestration. We would be pleased if we could provide our customers with the advanced services. Thank you.
Thank you, Hiroshige-san. I think you see the many significance of this POC and many insight of the business aspect and technology aspect of this POC. So now I'm also presenting about the deeper view of the technical aspect of our POC. So let me introduce myself first again. My name is Hiroki from NTT. I am Senior Research Engineer at Network Technology Laboratories. So, and I'm responsible for the future network architecture of whole NTT Group companies network, especially of network slicing. So today I'll give some detailed view from NTT R&D's perspective about this POC, starting with NTT's vision of the future network in 2030. And I would briefly talk about the significance of this POC and key components of NTT R&D products. So let's start with NTT's network vision targeting 2030. We call it as ION. ION stands for Innovative Optical Wireless and Network. NTT has been promoting research and development for ION in recent years. One of the key components of ION is all-photonic network called APN. Using APN, the direct optical connectivity service will be implemented to device-to-device communication together with network services and overlay solutions. So another aspect, ION proposes function-specific dedicated network called FDN. FDN is a logical network service over APN with various performance characteristics and functions. So it also supports flexible and dynamic control of the network service by combining service and cloud functions. This is a research background of ours. So the aim of this POC for NTT is to promote FDN concept as the evolution of end-to-end network slicing. So in other words, we see that end-to-end slicing will be the early adoption and implementation of FDN concept in 5G or beyond 5G network. So as you saw in this POC, we demonstrated 4 applications of different performance characteristics using end-to-end network slice. First, ultra real-time video analysis using AI requires relatively low latencies and medium bandwidths for high-resolution video transmission. That these requirements are high, but not so extreme. So then we proposed the second use case. The second use case was remote motion control using TSN, time-sensitive network. This application requires extreme performance in terms of jitter and reliability. So it is a typical use case of that requires end-to-end slicing to assure the performance. And xHaul is also the typical use case of end-to-end slicing because it requires extreme performance in terms of latency and throughput. The last use case of disaggregated computing using RDMA was the prominent use case of the future FDN, and its requirements is extraordinarily high. So the main technical point of this POC is dynamic and on-demand control of these high-performance network using E2E network slice under the control of LSO framework. So the key technology enabler is end-to-end slice controller. It immediately designs and configures and activates both of 5G domain and transport domain networks when receiving the service request from customers. This E2E slice controller can optimally design and monitor the quality of consisting 5G and transport domain slices according to specific SLA. This makes it possible to guarantee and manage low jitter and less than 20 microseconds for remote motion control, low latency and high bandwidth for 4 milliseconds, 200 megabps for distributed computing, and so on. So let me introduce the key technology components of E2E slice controller. The first one is a multi-layer transport provisioning engine. We call it MLTPE. It enables optimal resource provisioning for packet and optical networks in accordance with SLA. And MLTPE is implemented to work with ONF-TAPI reference implementation and MEF Presto SDK to control connectivity through packet controllers and optical domain controllers. And MLTPE is utilized to calculate optimal resource and path calculation for transport slices to meet the high performance requirements of mission critical applications. The second component is slice gateway. Slice gateway is the data frame function for end-to-end slice, aware traffic control, and route selection according to SLA conditions. SLG provides slice-aware differentiated traffic control by creating logical connectivity between SLGs to keep underlay network agnostic about slices. Slice gateway controller also provides REST API to enable on-demand and automated slice provisioning. The third one is Hammock. Hammock enables real-time monitoring of delay and jitter in a single system with a high accuracy that cannot be achieved with conventional technology. It enables advanced network quality assurance, communication service routing, and advanced maintenance and operation for post-5G communication services such as esports and telemedicine and so on. The last one is the CNF provisioning engine. We call it SCPE. SCPE enables automated and optimal container resource allocation for CNF in accordance with MEF Presto API and 3GPP network slice APIs. It designs the optimal amount of 5G functions resource for specific SLA. The performance for CNFs is predicted on the basis of machine learning-based performance model and solves optimal resource amount and continuously updates in accordance with traffic changes. And it also supports the multi-cluster deployment of CNFs for low latency and reliability on the basis of calculation of the SCPE. It works with many container control and operation software packages such as Helm and Kubernetes operator for instantiation, modification, and scaling and network slicing. So it works with multi-cluster and multi-site Kubernetes environment. So this is an overview of the key technology component from NTT R&D products. So I think it can contribute to this makes the study about end-to-end network slicing, and also it leads the market of the network slicing in the world. So this is my talk, and I think this will help the technical understanding of this POC. So now let's move to the significance of this POC in the local area problem solvement in Japan. So Noriyoshi-san, can you speak up with the technical, not technical, business use case in Okinawa area specifically?
Thank you, Papa-san. Thank you, everyone. My name is Yamazaki. So I'm a co-incorporator of Okinawa Open Laboratory. So as its name suggests, OL is active in Okinawa Prefecture, Island Prefecture, the most south side of the Japan. So Okinawa Island is 1,600 kilometers away from Tokyo. So there are various issues with network service in Okinawa, unfortunately. So today I tell the above so recent situation in Okinawa. So after the spread of COVID-19 from 2019, so the need for vacation has increased now. Many businessmen stay in Okinawa a long time and of course doing the remote work. So Okinawa, far from big cities, and warm island with a low population density, very good position, far from the big cities in Japan. So with this situation, so communication lines become very tight in Okinawa. So to the outside of the island, such as Tokyo, Osaka, or anywhere all over the world. So I say again, so Okinawa Island connectivity very tight right now. So we are having problems with our daily teleworking, unfortunately. So similar situations are occurring so nationwide in Japan. Probably the same things is happening all over the world, I think. So let's go back to Okinawa situation. So Okinawa Open Laboratory have a great member. It's Okinawa Cable Networking Corporation, the biggest cable operator in Okinawa Island. So we call the company name the OCN, Okinawa Cable Network. The OCN have a needs to provide network QoS service to seamlessly connect between the regional communication line with the nationwide communication network service provider, like NTT Communications, Tanaka-san's company. So our technology will solve such problems, I believe. So by using the end-to-end network slicing technology, of course, combined with the easy orchestration technology of multi-domain networks. So hopefully, so this year, Q3 or Q4 or something like that, so Okinawa Cable Network collaborate with NTT Communications, some other nationwide network service provider, will provide an end-to-end QoS commitment slicing technology service in the future. So anyway, after the COVID-19, let's come Okinawa Island, very cozy place and good for vacation. Thank you.
Noriyoshi-san, I think we covered the business impact for the service provider and technology aspect of the network slicing, and we also covered the Okinawa area local problem meant from the end-to-end network slicing.
Yeah.
So that would be our panel discussion first, and so I think we can move to the live Q&A session. Thank you for joining the panel discussion.
Thank you, gentlemen. Very good discussion there. And yes, Niroshi-san, we'd love to come to Okinawa when we can finally travel and meet you folks there. Great job. We're going to move to the panel now, and Daniel Barlev, MEF's VP of Strategic Programs, he also doubles as our MEF 3.0 Proof of Concept Program Director. He's no stranger to MEF POCs, having developed the MEF POC program 7 years ago in 2014. And so Daniel, I'm going to turn it over to you to host the panel here today.
Thank you very much, Kevin. So welcome our panelists back for the Q&A. This is a very powerful POC combining network slicing and 5G, very demanding performance that's required. So as we wait for them, I think, yes, they're joining us now. Great. Thank you. So the first question for you, I think, Baba-san, is there a reason why the service orchestration functionalities, you showed them being interconnected using LSO Sonata rather than LSO interlude APIs? Can you expand on that and explain what the decision process there was?
Okay, thank you, Daniel. I think that's a good question to start with this live Q&A session. So first of all, I'm senior research engineer in NTT Lab, and I'm working in the future or next generation network architecture department. And the network slicing is really the central part of my work. So regarding the question, we assume that the 5G core service provider and transport service provider is as a different organization. So that's why we use the SOF for the interworking between two providers. And we also used the orchestrators from OOL, and they implemented the bus part and soft part in a single product. So it includes two parts, bus and soft. And for the interoperator orchestration between the bus part is done by Sonata. So network slice ordering for 5G core domain and 5G transport domain order is processed in Sonata. But as the question is part of the question, and I think the person who asked this question is right. So the business process is done by Sonata, but generally the resource handling or resource orchestration is done by interlude. But we are not we have not done about the interlude part. In this POC we have shown the Sonata part for the interoperator ordering in the transport domain and 5G core domain. Thank you.
Okay, great. So it sounds like the Sonata and interlude are in a way combined from your point of view, using OpenNEF. So you're not differentiating between them, but you are supporting orchestration across multiple domains. So a question for Hiroshiga-san, perhaps. It was mentioned as one of the use cases, the automated guide vehicles, AGV, and the Industry 4.0. Can you elaborate perhaps about other use cases beyond what was described in the AGV use case?
Okay. Exactly. I said the AGV is an example use case as smart factory. In other fields, the haptics communication in remote control for construction machines is one of the use cases. In this use case, we have to handle several data traffic, such as wide bandwidth video streaming for virtual reality, and the low latency and huge amount of telemetry data for feedback for operation. Thank you.
Okay, thank you for that, Hiroshiga-san. So another question, or it's a point that was made. It's a very impressive POC. Thank you for that. When it comes time to commercialize this capability, who is in charge? Who owns the customer? Who assures the SLA for each slice? I'm guessing that's going to be NTT facing the customer. Perhaps one of you could answer that question.
Yeah, okay. As I said, in the first place, our company focuses on the smart factory market. For our customers, network slicing is one of the key technology utilizing with private 5G. Network slicing should be versatile in several industries, for example, smart health and smart city and so on. And from our customers, we have a lot of requests to carry on the field POCs, and we already started private 5G POCs with our customers, such as machine tool company, industrial factory, and several companies. We would like to prepare to provide network slicing with private 5G solution and service to meet their demands. We would like and we would be pleasure if we could provide our customers with advanced services. Thank you.
And is this a solution in production in Japan? You mentioned the trials of private 5G with network slicing, but is it yet a commercial offering?
Yes, but we. Yeah.
May I explain about that?
Of course.
It's okay, Tanaka-san?
Okay.
Yeah, excuse me. So I had in my presentation, the Okinawa Prefecture have some local cable originally CATV network service operator. The biggest one is the OCN, Okinawa Cable Network Corporation. So they already have various kind of the hotel network service. So originally, of course, their main network technology based on the coax cable network and fiber to the somewhere. But at the same time, right now, they want to implement wireless last access network service in Okinawa area. This condition is not only the Okinawa Prefecture, also the Japan nationwide, many local CATV operator want to do the same kind of the wireless network access connectivity delivery to the market. So the many cable operator want to implement private, not only the private local 5G network service, also the want to implement the end-to-end network quality guarantee service to the edge side, to the central video server or something like that. So that is so last question there. Who is want to implement the commercial level? So my answer, so many local CATV operator in Japan want to commercialize this kind of the end-to-end network slicing and the quality guarantee network service technology.
Okay. And
is it make sense of the answer to you?
Yes, thank you. And perhaps we'll just expand on that. Specifically in Okinawa, where you're based, are you seeing particular network services that are starting to be discussed as a result of the COVID-19 situation? I think Okinawa is quite rural.
Yeah.
Perhaps there's a sort of a change in the market that you're identifying as a result of COVID-19?
Yeah. So right now, no tourists, but many vacation people come alive Okinawa. So these kind of the people's requirement are practical business use network quality. So mainly video communication, like using our this application. Yeah.
So more
probably,
and more people are relying on high quality network services for
yeah. So not only the big pipe, also the, how can I say, quality guarantee, stable quality guarantee network, their requirement.
Okay. So another question that's come in is, I think this is for Baba-san. What are the technical issues to be solved when delivering an extreme service? When you're using, when you're delivering time-sensitive networking and RDMA, because that seems to be very, very demanding, especially in Industry 4.0. So could you expand on what the technical issues that you faced when implementing that?
Okay, thank you for the question. And as shown in the demo, TSN is the base protocol required for mobility control and industry equipment and LZVs using communication network. But these protocols are intended to be used only inside the factory networks and were never used in network-wide. So however, with the advent of 5G and the support of TSN by 5G systems, we are seeing the next generation, in which people and AI can control robots and devices remotely via the network. So, and as you know, there are very high expectations for this in Industry 4.0. So such use cases require very precise, cyclic, and strict control of packet transmission intervals and strict guarantees of arrival times to the clients. So, and despite delay as severe as 2 millisecond minimum and jitter is said to be at the level of several nanoseconds or microsecond level. So in order to guarantee this kind of communication over a wide area network, jitter cannot be suppressed by processing in packets. So it will be necessary to occupy resources such as optical wavelengths in optical layer 1 and connect them in an on-demand and efficient manner using optical network. Same as in the RDMA, it is mainly used in the data center network to disaggregate the compute resource. But disaggregation over the network makes requires huge bandwidth or low latency. So same as the TSN, RDMA needs also a high capacity and very stable network to implement the disaggregation of the computer resource over the network. So for this reason, I believe that providing multi-layer services include not only traditional carrier Ethernet and IP or SD-WAN, but also layer 1 transport will be the key to provide promising future use cases such as smart factory and disaggregation of the computing. So in order to realize such a completely new world, NTT is not only increasing the capacity and low latency or lower power consumption of optical transport, but also conducting a research and development on flexible control of optical transport network and its architecture. And we have successfully shown this in this POC by configuring layer 1 connectivity for services of TSN and in the demonstration as an example of dynamic allocation of optical transport resource.
So what you're talking about is a very powerful combination, not only of private 5G, network slicing, local 5G, but also optical transport. You see that as a very important component in the end-to-end extreme services.
Right. Yes. Thank you for summarizing my answers. Yes. What I want to say is that not only for 5G, and we need to combine the transport part and especially layer 1 or multi-layer things is critical to implement the extreme services.
So I think we've got time for one question which I'd like to pose, and that is NTT and Okinawa Open Lab have been very involved in the work of MEF and not just doing this proof of concept. And standards look like they are a very central part of the success of this these use cases and these implementations. Can you elaborate on where you think MEF needs to focus in terms of standards work? Because we're doing network slicing in MEF 84, that there's work at LSO Sonata, LSO Interlude, and other places. What do you think are the, let's say, the top 2 or 3 areas of work that MEF need to focus on in order to allow you to keep moving forward with this at the speed that you want to?
Okay, I'll take the question. So as you know, end-to-end slicing is key of the future network services. And even if we say end-to-end, there is always multiple layers or multiple domains for such as metro or core or 5G domains. So we need to interwork each domain or orchestration. So we see that I believe the common language among domains and operators is crucial, and so standards need to define the common, so to say, language for the service providers to keep the assured quality of the network slicing. So I believe that this is a role of that MEF standards play in the significant slicing context. As you mentioned, the network slicing project in MEF and subsequent work of network slice attributes very effective as a common model between the service providers or technical vendors. So I believe that this will accelerate end-to-end slicing in a true sense of the word. And I will be happy if this POC can accelerate these studies. And I also be willing to contribute to the project.
And I think we're also seeing on that note, Baba-san, the idea of having network as a slice as a product payload in LSO Sonata. So I think that ties in as well to what you were describing in terms of network slicing profiles and so on. We've run out of time. We don't have time for more questions right now. So I'd like to thank you very much indeed, Hiroshige-san and Baba-san and Oriyoshi-san for joining us today and demonstrating this very impressive POC and answering our questions. So thank you very much. I will now hand back to Kevin to complete the POC, and I'll just highlight that there's a very powerful white paper associated with this, Kevin, that I think you have on the slide. So I just want to point that out because a lot of the information related to this POC is in that white paper. Back to you, Kevin.
Yeah, great. Thank you, Daniel, and thank you to the team. Wonderfully was when during the introduction, the objectives of the POC were laid out. That really helped us to frame what this POC was all about because there's so much being shown in such a short period of time. The automated provisioning of services across the different transport domains, end-to-end performance capabilities of the different slices and performance management and so on and so forth, the use of MEF APIs, the use of MEF services and so on. So it all really came out. I thought the use cases were great when you can think about it. And I said this in one of the other POC recaps. We had, on one hand, you have got these very contemporary use cases, such as the congestion, the performance issue with Okinawa. On the other hand, we saw how this fits into the forward-looking plans for NTT with their 2030 strategy. And 2030, wow, it's a long time away. It'll be awesome to see how our work and the work of our partners here plays out over time in that regard. I think, and this was where I think it concluded with the discussion, the kind of overriding most important theme that I saw here was that the importance of the end-to-end slicing capability, being able to manage the different domains, private 5G transport and so on. And it really underlines the importance of the MEF work that we're doing to define that, the slicing above the transport domain. And we've seen a lot of different use cases across all the POCs, and this one was phenomenal. So, with that said, I'm going to close out today by just bringing up the, letting you know that there is more information available on our public website. You can go to mef.net/POC/138, or you can just Google MEF, you can just Google MEF POC 138. And on that page, there's the white paper that Daniel mentioned, overview, network diagrams, other materials, blogs, and this POC will be available on demand on that page very soon. So if you like what you saw today, please have your folks go to that page. And as we wrap up today, I want to tell you a little bit about the MEF 3.0 POC Awards. Each of the POC teams is eligible. We have 4 categories covering innovation, business impact, market game changer, and judge's choice. And then they're going to be judged by a panel of 8 independent analysts. As I was watching the POC today, I thought, you know what, this one would win the award for most new acronyms if we had such a category. That was pretty cool. We'll be announcing the awards during episode 3 of the MEF Infinite Edge series on March 10th, so please don't miss it. Now, if you want to carry on the conversation with the POC team, you will see information on the slide, which gives you a URL, and so you can jump into conversations by clicking on that URL, or dumping it into your browser and going to that site. But there's also contact information on the slide as well as a URL to the white paper that was mentioned. So with all of that said, I really want to thank the POC team for all of the heavy lifting that they've done to put this great POC together. Of course, the MEF production team as always, and most importantly, I'd like to thank you for attending this MEF 2021 MEF 3.0 POC showcase. Thank you very much.